Good morning, students. After a long gap, I'm here to talk about the nucleophilic substitution reactions, which I had a long time back had taken. And I think we had discussed with the SN1 reaction. I hope you are clear with the SN1 reactions. So you know that the substitution reactions can occur by two mechanisms. One is the SN1, another one is the SN2. So first one is SN1, which is substitution, nucleophilic and unimolecular. And it follows the first order kinetics, and the rate of the first order depends only upon the concentration of the substrate. And what happens in SN1 reaction is the first thing is that CX bond undergoes hydrolysis in the first step, that is dissociation. Then the positively charged carbon that is produced in the first step, which is called as carbocation, and in the second step the nucleophile attacks the carbon to give the respective product. So here we can see an example wherein you have your alkyl halide. This is actually a tertiary alkyl halide, which when reacted with water, or the water will act as a nucleophile, the OH minus, giving you the tertiary alcohol. This is the reaction. And now what is the mechanism here? The first step is that between the carbon and halogen, the dissociation takes place to form the carbocation, and this step will be a slow step or the rate determining step, and the next immediate, the OH minus will attack the carbocation to give the alcohol. And this is the energy profile diagram, which I had in detail had explained to you in the previous slide, so I'm not going to go into it. You can see that energy profile diagram has a graph like this. And this is as the nucleophile approaches the alkyl halide, the energy of the system increases, or the dissociation takes place to give you the carbocation. This is the place where you have the carbocation, the energy is less. Then the nucleophile approaches. As the nucleophile approaches, that a kind of transition state is expected here, and that's why the energy is very high, and it follows the product is formed and the energy decreases, and this is the place where you have your product whose energy is lowest. Now, so here you can see that it is then S2 halobutane, right? S2 halobutane. What do you mean by this? Yes, it is the absolute configuration of this particular molecule, where you have the regarding this we will be discussing in stereochemistry in final year. So time being, remember this is an S configuration. The 2-halobutane, when reacted with water under SN1 conditions, we find you will get two types of products. One where the configuration is retained. See, this is also S here, this is also S here. Whereas another one, you have configuration inverted. Now what happens here is you will get the carbocation, the incoming nucleophile. If it is going to attack the carbocation from the front side, you will get the retention in configuration. If it is going to be from the back side, then you will have your inversion in configuration. So two common side reactions that are possible in SN1 reaction is the elimination reaction and the carbocation rearrangement. Now what do you mean by elimination reaction? If you have a halogen present here, then there will be elimination taking place to give the alkene, and it is not in your syllabus. Just remember that you can also have rearrangement. The carbocation will rearrange itself to give the most stable carbocation. Now among the three carbocations, that is your primary carbocation, secondary and tertiary, the tertiary is considered to be more stable. So it will shift itself in such a way that you get the more stable carbocation, and it will give the corresponding product. Now factors which affect the SN1 reaction, you have effect of solvent, leaving group and substrates. Okay, these three are the main things that are you see in the substitution reactions. Now when you have a halogen attached to the R group, we will be calling that X as the leaving group. Okay, and that Rx will be called as the substrate. Now coming to the effect of solvent, you know, any reaction to take place, we always go for homogeneity of the reaction. So people will naturally will have solvent in which the nucleophile and the substrate dissolve, and those things are called as solvent. And you can have two types of solvents. One is polar solvent, another one is the non-polar solvent. Now when you say polar solvent, it is your water is the best example, where you have got plus and minus together, right? And then you will have non-polar solvents where you do not have this kind of polarity present in the solvent. Then what kind of solvents prefer SN1 reaction, or SN1 reaction prefers what type of solvent is? The polar nature of the solvent helps to stabilize the ionic intermediates. That is, the carbocation that is formed will be stabilized by the solvent. And protic nature of the solvent helps to solvate the leaving group. That R and X is there, right? So this protic nature of the solvent will try to solvate. Okay, that is, it will make a heterolytic fission between the R group and the halogen. Now the examples of solvent that are used in these reactions are water and alcohol. These are the common solvents that are used in SN1 reaction. Now in some of the cases, the solvents themselves will act as nucleophiles. Next you have your leaving group. Now when you have your leaving groups, I said Rx, this X can be anions or cations or neutral molecules. It is important that the leaving group stabilize the additional electron density that results from the bond heterolysis. Okay, that particular leaving group should and must have the additional electron density that should be able to bear that additional electron density that results from bond heterolysis. Then the common leaving groups are halogens, and also you can have sulfonate esters such as tosylate. Okay, what is tosylate? You will have your benzene, right? So if methyl group is attached, you call it as toluene. And if you have your sulfonic acid added to that, then you will be calling the paratoluene sulfonic acid. Okay, and that O group, it can act as a, or the whole moiety can act as a leaving group. Okay, and you can also have common neutral molecules as leaving groups such as water. So this is about leaving group. I hope I made myself clear about solvent and leaving group. All you have to know is, in case of solvent, you require polar nature, and also it should be the protic nature the solvent should have, and the common solvents we use are water and alcohol. When you talk about leaving group, the leaving group can be anion, cation or neutral molecules, and they should be able to bear the additional electron density that result from bond heterolysis. Rx is there, right? So that will dissociate, and X has to have the capacity to bear the excess electron that is given from the bond breaking. Then the common leaving groups are halogens and the sulfonate esters. Then the common neutral molecules can also act as the leaving group. Now the relative ability of X as a leaving group is influenced by following factor. That is the strength of Rx bond, the polarizability, and the stability of X as a leaving group. As I said earlier, it should be able to bear the excess electron that has been given to it by the bond breaking. Then the degree of stabilization through solvation and the transitions of the solvation of the forming X in the transition state. Then the reactivity order for the alkyl halides Ri, Rbr, Rcl and Rf is least reactive. Okay. Now why we say that Rf is least reactive and Ri is maximum reactive? Because the size of your iodine, it's bigger in size. So naturally it will have the bond length between R and I is going to be, it's a very, very weak bond, and hence it can dissociate very easily when compared to that of the other halogens. So whenever people take up the substitution reactions, they will take the substrates to be alkyl iodides rather than the bromide, chloride or fluoride. Coming to the nucleophiles, the nature of nucleophiles has no effect on the rate of SN1 reaction, because the slowest determining step or the rate determining step is the dissociation. Okay, the first step wherein the Rx will dissociate to give R plus and X minus. And all carbocations are very good electrophiles. Why do we say very good electrophiles? They carry positive charge. So naturally they will be hungry for the nucleophile, right? So they will react immediately to give the corresponding product. So this is the point about the nucleophile. The nature of the nucleophile has no effect on the rate of the SN1 reaction. If you have any doubt regarding this, please do call me and ask, and I will explain it to you once again. Don't neglect any part of the topics, because you do have your internal examinations that will be on when the final years are writing that semester examination, you will also have to write your internal exam. So you just cannot neglect any of the topics saying that no, we don't have the final examination. So the internal marks will be considered for your final semester exam. So please take it seriously and study for the internal examinations. Now coming to the substrate, the rate of the reaction depends on the structure of the alkyl halides. So here we see the tertiary alkyl halides. When you want to have your SN1 reactions, you have to select your substrate to be tertiary alkyl halides. Why tertiary alkyl halides? They are highly reactive because the resultant carbocation is stabilized by 3 electron releasing group. You do have your hyperconjugation coming into play then. And allylic and benzylic halides can also react by this mechanism because they also form relatively stable carbocation. Then phenyl halides do not undergo SN1 reaction. What do you mean by phenyl halides? The chlorobenzene. Because you cannot have the phenyl cation, isn't it? So you have your aromatic nucleus which is having pi electron cloud, and you cannot expect the positive charge on the top of the carbon atom that is there in the benzene nucleus. So it is going to be least reactive for SN1 reactions. Right? So with this I will just pass on to the next mechanism, that is the SN2 mechanism. Now what do you mean by SN2 mechanism? It is nucleophilic substitution and bimolecular. The rate of the reaction is a second order and depends both on the substrate and the reagent. The substrate and the reagent. Now these reactions are completely in a single step. Okay, please note it is in single step, whereas your SN1 reaction it was in 2-step. Okay. Now there is a leaving group and also nucleophile here too, because it is your nucleophilic substitution reaction, and no intermediate is formed, but you do have your transition state. Now when you have your nucleophile, let us take this substrate, and let us consider this as the nucleophile. Now in this reaction, the SN2 reaction, it is a single step reaction wherein the nucleophile will attack the carbon from the side opposite to that of the leaving group. Now look at this substrate. Which is the leaving group here? It is your chlorine. So this is your nucleophile. So you can see there are lines drawn in a different manner. You can see a straight line and a darker line and then dotted lines. Now what do we mean by this? It is a 3-dimensional way of representing a compound molecule, and this we call it as the configuration of the molecule. That is a specific arrangement of atoms around the carbon. One has to note that it is a specific arrangement. There is no change in the attachment of the groups to the carbon atom. So here what happens here is, you call this as the leaving group. As the leaving group leaves the carbon, the incoming nucleophile will attack the carbon from the side opposite to that of the leaving group. So this is the opposite side leaving group, right? So it will attack over here. So what happens here? So as the leaving group leaves the carbon, there is a bond dissociation taking place between carbon and halogen. So this is it's becoming lengthier, and there is a new set of bond being formed between carbon and bromine, right? So and one more thing you have to observe is, this carbon is sp3 hybridized. So as the nucleophile attacks the carbon from the backside, there is change in hybridization of this carbon. So from sp3 it goes to sp2. So this is a tetrahedral carbon. When you come over here, it is going to be trigonal, and all these 3 atoms will be in the same plane at 120 degrees. So as the leaving group leaves the carbon, all these points please do make note of it. So as the leaving group leaves the carbon, the incoming nucleophile attacks the carbon, and this is a transition state where the configuration of this carbon has changed from sp3 to sp2, right? And this Cl will leave the carbon, giving you the inverted configuration. Okay, and we usually say the inverted configuration example what we give is, on a windy day you open up your umbrella and walk, and if the wind is going to blow from the opposite side, what happens? The folding umbrella, it turns upside down, right? So there is inversion in configuration taking place. You understand? So even in this molecule, the same thing happens. As the bromine comes and attacks this carbon, all these groups configuration gets inverted. That means you will have your methyl group here, and this will come over here. And if you mark this H1 and H2, then there will be you can observe the inversion in configuration. Now this is actually not an asymmetric carbon atom. If you take an asymmetric carbon atom and speak about the SN2 reactions, now the asymmetric carbon atom will be optically active, and if you say it is going to be dextro, the end product will be LEAV. So the example I have given here, the methyl halide, sodium hydroxide giving methanol and sodium halide, and the rate of the reaction is dependent upon the alkyl halide and the nucleophile. See, alkyl halide and nucleophile. So the carbon hybridization is sp3, it goes to sp2, and you can see it is sp3. I have not written any of the groups over here. If you find a line like this and none of the groups have been written, that means it is methyl group. Please make note of it. Or you can just substitute by, if you want to say this is going to be hydrogen, then you have to write over here hydrogen. Okay, I hope I am not rushing up. Please do try to understand. The OH minus attacks this carbon from the side opposite to that of the leaving group. This is a transition state wherein the carbon has undergone sp2 hybridization. Then it reverts back. You can see the configuration has been changed over here, right? So you will get the product with the inverted configuration. Now this is the energy profile diagram. As I discussed in SN1, the same thing happens here. This is the starting one and it goes up. This is the transition state where you have a higher energy, and then it falls back to give the product. And all this has been discussed over here, and even in the textbook you are given this particular discussion. And once I complete this topic, I will send you the PDF of this. I think in the textbook a lot of unnecessary things are given there, so you can just follow this. And I have given it very briefly, so make use of these notes for your study of this particular topic. Now this is the stereochemical features. As I discussed earlier, when a substitution takes place in a chiral carbon, inversion of configuration occurs, and this was observed by the scientist Walden, and hence you will be calling it as Walden inversion. Please note, it is called as Walden inversion, and the example is given here, a beautiful example is given here. So there is inversion in configuration. Now this is actually Walden observed in chiral carbon. Here it's not a chiral carbon. You yourself can write a chiral carbon and write this reaction and then explain about Walden inversion. In SN2 reaction, alkyl halides are converted into alcohol in presence of strong base, which results in inversion configuration. The change of configuration is established by observing the directions of optical rotation. So you will have this as the plus optical rotation, and here you will have your minus. If it is going, this is going to be minus, then the end product will have plus. Now factors influencing SN2 reaction. Just like in the other case, we discussed about the polar solvents, they help the SN1 reactions. Now coming here, the protic solvents or the polar solvents, you will be having, they slow down the SN2 reaction, just opposite to that of your SN1. Polar aprotic solvents such as acetone, okay, it's polar aprotic solvents. There is no hydrogen. Give any species that can give off hydrogen, you will call it as protic solvent. There are solvents which can easily give hydrogen, you call it as protic solvents. So if you have polar protic solvents which contain strong dipoles but no OH or NH2 group, speed up the SN2 reaction. The non-polar solvents like hydrocarbons, benzene, toluene, etc., the SN2 reactions are relatively slow in non-polar solvents. I think I made a mistake there saying that non-polar solvents favor the SN2 reactions. It's actually polar aprotic solvents, they favor the SN2 reactions. Please make a note, I made a mistake when I was discussing SN1 reaction. The non-polar solvents actually they slow down the SN2 reaction. So the feasible condition for SN2 reaction, it is polar aprotic solvents. Effect of leaving group. The leaving group usually has a negative charge. The group which stabilize the negative charge are the best leaving groups. That is, the weakest bases are stable anions as anions and are best leaving groups. Now here I have given the effect of nucleophile. The better the nucleophile, the faster will be the SN2 reaction. The best nucleophiles are the best electron donors. The table is given here. Nobody will ask this table. This is only for your understanding. All you have to know is the better the nucleophile, faster will be the SN2. The nucleophiles with the best electron, the best nucleophiles are the best electron donors. So here I have given the list of nucleophiles which are good for SN2 reactions. So you yourself, I think, can make a relative study about this. Effect of substrates. Activation energy of the transition state in the reaction increases as the steric hindrance in the substrate increases, while at the same time reaction rate is decreased. And for SN2 reaction, the order of reactivity is you will have to prefer primary alkyl halide rather than secondary, rather than tertiary, because it's very clear. Now when you have your tertiary alkyl halide, you will have 3 bulky groups attached to the carbon, right? Now the incoming nucleophile to approach this carbon, it's going to be a difficult task. Okay, I usually say the carbon is sp3 hybridized, so it will be in tetrahedral shape. Imagine you have 3 methyl groups attached to the carbon, which you are expecting it to undergo SN2 reaction with the nucleophile. Now since you have the 3 methyl group, even they are sp3 hybridized, so you will have 1 umbrella and attached to it 3 umbrellas. Okay, so incoming nucleophile, it is very difficult to approach the carbon, right? So that is why the order of reactivity is primary is more preferred, wherein you don't have that much of steric hindrance compared to that of secondary and tertiary. In case of secondary and tertiary alkyl compounds, SN2 reactions is largely superseded by an SN1 reaction or elimination. Please make a note. This is a very important statement when we discussed about the mechanism of SN2 reactions. In cases of secondary and tertiary alkyl compounds, SN2 reaction is largely superseded by SN1 reaction. So they prefer SN1 reaction rather than the SN2. The rates of SN2 reactions of allylic and benzylic are also increased because of resonance in the transition state. So this is also another important point for SN2 reactions. And I think with this I complete the SN1 and SN2. This is a tabular column which shows the differences between SN1 and SN2, and I did not discuss, you yourself can tell. SN2 is a bimolecular, this is a unimolecular, it is a one-step mechanism and it's a two-step mechanism, and there is no carbocation rearrangement, whereas in case of SN1 there is carbocation rearrangement. I told you to get the most stable carbocation there will be rearrangement, and here in this case there is inversion of configuration, whereas here no inversion of configurations, and the order of reactivity I have given here primary, secondary and tertiary, whereas it is going to be once again, but in this case the primary will be more reactive, whereas in this case tertiary will be more reactive. If you want, you can write it the other way around. Okay, so I think with this I complete the topic of nucleophilic substitution. I'll stop here and continue about elimination reactions in my next video.